This is Exploring the Solar System Part 6, the final part of the trilogy. And it's talking about origins. You might think this ought to have come first, but actually I think this is the most difficult part of the whole set. And so I left it till last because I wasn't even convinced I wanted a Part 6. I thought I might conceivably leave it at Part 5. For the origins of the solar system, this is all conjecture. So with how does the sun work and what's going on in the solar system and what's happening with rovers on Mars, they are all essentially facts. This one is, we live in a solar system and we know what the solar system looks like now. Can we figure out how it came to be? And it is still conjecture, it is still hypothesis, and some people believe that what I'm going to tell you is wrong, in the sense that we really are still struggling to try and get to grips with exactly how do you make a solar system. So I'm talking about how our solar system formed, what clues we have that tell us how the solar system formed, and of course we can't do an experiment, we can't make another solar system to see how it goes. We're relying on simulations of, if we start like this and run a simulation, do we end up with a solar system that looks like the one in which we live? It's a bit like doing simulations of the universe, where you're starting with the Big Bang and then seeing, do we end up with galaxies like we see in the universe? It's the same sort of thing on a smaller scale. Let's start with something where a star is forming. Can we figure out how that leads to a planetary system that we know and love? And there are still many questions that remain. So a little while ago, I brought you a brass orrery and said, look, isn't this nice, seeing all the planets go round in their orbits? When you build a model of the solar system, it's built from effectively the inside out. This particular model here, for instance, you start by building the sun, and then you add Mercury, and then you add Venus, and then you add Earth, and then you literally build the orrery up, starting in the middle and getting the more and more distant planets. So that's fine for building an orrery, but that is not how the solar system formed. We are fairly convinced that that is not how it actually works. Now, here's a picture of a star cloud called Rho-Ophiuchi. It's one of my favorite astrophotography targets. I took this image a couple of years ago. This particular cloud complex is about 400 light years away, and it's actually one of the closest star-forming regions to us. So in that sense, it's been well studied, because although there are star-forming regions throughout the Milky Way, and of course in other galaxies, this is actually only a few hundred light years away, so it's one of the easiest ones to study. We think that hundreds of new stars are being born in this cloud. You can see the size of the cloud. There's a scale bar of 5 light years, so it's clearly tens of light years or so in diameter, in size. And we think that many new stars are being born, perhaps enough material there in that particular cloud to make many thousands of stars. And we believe that our sun and our planets were probably born in a cloud much like that one. So here's a time scale, a timeline to try and help us understand what actually happened. So taking 0 as being when we start with a large cloud of hydrogen and we allow that hydrogen cloud to collapse. A trigger for the collapse might be that a supernova went off and sent a shockwave through the cloud. It might have been triggered by galaxy collisions. It looks like there's evidence now that a galaxy collided with the Milky Way 5 billion years ago, and maybe that collision is what actually prompted a cloud to collapse to make our sun. Again, that is simply conjecture at the moment. But if we take the clock to start when the cloud started collapsing, it'll take a while for the cloud to collapse. But during that phase, I've written there at the top there, T Tauri, that's the name of a star that we've studied, and that's now given its name to, whenever a cloud collapses, it is going to heat up the core of that cloud, and we call that stage of stellar evolution a T Tauri stage. And even before the sun has actually ignited, i.e. before it's hot enough to actually fuse hydrogen into helium, it'll still be getting quite hot, and it might take millions of years of heating before the sun gets hot enough to actually ignite. It's not often appreciated that it might actually take 30 million years before the sun actually switches on. In other words, it's a little hot clump of gas in the center of this cloud, but only after perhaps 30 million years do we actually get the thermonuclear fusion, which puts the sun in the middle of the main sequence on our diagram there of luminosity and surface temperature. We think planets might actually form before the sun has switched on. I'll come back to the timing of that just shortly. But as I said earlier, the Rho-Ophiuchi cloud complex is a cloud that's big enough to form maybe thousands of stars. And we think our sun was probably born with thousands of siblings, mainly because that seems to be the way it happens. Whenever we see stellar nurseries, they always seem to be large, and they always seem to produce hundreds, if not thousands of stars. So it's reasonable to assume that our star, our sun, was born with a huge number of stellar neighbors. But over time, for one reason or another, our star has drifted away, or at least maybe all of the stars have drifted away from this cluster and have all gone their own merry way around the Milky Way. Given this happened 5 billion years ago, it's effectively impossible to backtrack and work out which other stars our sun might have been born with, which are the siblings of our sun. But we know the sun is a lone star, and we don't believe that stars are born alone. We think they're always born with siblings, and so they've drifted apart. And that might have taken a substantial amount of time as well. As you see here, perhaps hundreds of millions of years for our sun to drift away from its siblings. Hundreds of millions or thousands of millions of years, that's only a billion years. That's obviously only a short time in the 5 billion year history of our sun. So it's effectively ancient history, and we can't figure out, it's just a hypothesis. But we do know that stars are being born, for instance, in the Rho-Ophiuchi cloud cluster. The Hubble Space Telescope has taken a very close look at one of the stars buried deep into the Rho-Ophiuchi cloud, and they've seen this rather unusual UFO-type creature here. It's actually a star that's obscured by the dust that exists. Whenever you make a star, by taking a cloud and compressing it down until a star ignites, you will inevitably end up with a disk of debris and dust that's left over from the previous star's generations. And in this particular case, the dust is so dense you can't actually see the star itself. But you can see starlight reflecting above and below that plane. Starlight is being scattered by the dust above and below the plane of the star in formation. Like the Milky Way, whenever you take a cloud and collapse it, you will end up with a pancake. Doesn't matter what shape cloud you start with, if that cloud is rotating, and virtually everything in the Milky Way is rotating, you could argue pretty much everything in the universe is rotating to some extent or another. As soon as you start collapsing, like an ice skater bringing their hands in, it'll rotate faster and faster, and you end up with a pancake structure. So the actual plane of what in this case is the planet formation around this star is so dusty we can't see the star, but we can see starlight scattering off what is condensing to make that star. We know this is the case because we can see these dusty regions, these so-called protoplanetary disks, disks of dust and gas that haven't yet formed planets, but we are pretty sure are in the process of forming planets. This is one of the best images we've been able to see of a star with lots of apparent rings of dust around it, no signs of dots that indicate individual planets, but we can quite believe that if this is what it starts out like, eventually these dusty rings will condense and form planets if left alone. And that, although that's a rather nice image, it's by no means alone, because we've seen hundreds of these protoplanetary disks around other stars. The stars have to be close enough that those disks are large enough to see, so we can't see them around billions of stars in the Milky Way, only some of our nearest neighbors, but they seem to be ubiquitous in the sense of whenever we look out into the universe and see individual stars forming, we can see protoplanetary disks as well. These were imaged not in the visible part of the spectrum because protoplanetary disks are relatively dim, but they are still warmed by the star in the center, and so they tend to radiate in the infrared. So these are images that have been obtained from the ALMA, the Atacama Large Millimeter Array, which is sensitive to the infrared rather than the visible, which makes it much easier to see planets in the process of formation. So if we start with a large disk of gas and a little bit of dust, the dust is left over from previous stars, heavy stuff. Heavy means things like carbon and silicon, not just hydrogen and helium. There'll be lots of hydrogen and helium in the cloud, but if the cloud is the result of previous generations of stars, they would have made heavier elements. So there will be carbon and silicon and other elements in there as well. So if we start with tiny dust grains, perhaps even just a few atoms, nanometer size, they will eventually stick together to make grains that are micron size, which will then stick together and make pebbles, which will then stick together and make planetesimals and protoplanets. So the names here, pebbles, planetesimals, protoplanets, are just convenient names that we give to objects as they grow in size. There's no particular hard and fast rule as to when does a pebble become a planetesimal. You can see a rough indication of the size there from grains that are micron size, too small to see, through pebbles that can be centimeter size, up to small planets which can be the size of asteroids, which eventually grow into much larger planets. And just to give you an idea of where the Earth sits and where Jupiter sits, the little pictures there aren't the right size, but the arrows tell you where the Earth would sit on that scale and where Jupiter would sit on that scale. So we think we start with tiny grains of dust which coagulate together, stick together, and form these very irregular dust grains which are sort of micron sized. That's 1/1000th of a millimeter or so. And if you wait a while, those will stick together and start to make pebbles. You can see that they are, whenever they touch each other, they tend to stick. These are due to atomic forces. Rather than bounce off each other, they'll tend to stick to each other as long as they're not moving too fast. And the density is such that you'll get lots of these interactions, and these little tiny objects will grow and grow and grow until they become large enough to be something close to spherical. When an object is large enough, gravity will make it spherical because it won't allow it to be anything else. If there were any irregularities, they would be crushed under gravity. So to say things get built from small to large is fair enough, but we really need to get our ideas of, well, how long does it take for that process to happen? So let's put it on the same time scale that I showed you earlier. We think that dust will have been around right from the outset of star formation, and it might take millions of years to form objects which are kilometers or bigger, in other words, asteroid-sized objects, and it will take tens or perhaps hundreds of millions of years to make objects the size of planets. But that basic idea of they grow like that at that sort of speed can't be right, because if we think about the Earth and Jupiter, that would imply if things simply grow from small things to big things, that would imply something the size of the Earth would be made first and something the size of Jupiter would come along much later, because Jupiter is significantly more massive than the Earth. But that's not what happened. We are fairly convinced that the Earth didn't form before Jupiter. So that is not what is happening. So we have to find some idea of how can we explain how Jupiter didn't form last, despite the fact that it's the largest planet. The key either observation or the key factor that gives us an idea of the order in which things happened in the early solar system is the so-called frost line, sometimes called the ice line, sometimes called the snow line. It's the line at which hydrogen ices can exist. It's not a fixed distance because it will depend on the star you're dealing with and how much radiation is coming from that star. For the early sun, we think 5 astronomical units is where the frost line sat. In other words, anything between 0 and 5 astronomical units from the surface of the sun, you wouldn't have any hydrogen ices, you wouldn't have any water ice, you wouldn't have any methane ice, you wouldn't have any ammonia ice. Basically, it would be too warm. That close to the sun, it would be too warm. You would only have vapor, you would only have gas. So you'd have lots of hydrogen, helium, and also some carbon, nitrogen, etc. floating around as gas up to the ice line. But beyond the ice line, in this case beyond 5 astronomical units from the sun, you would get these hydrogen ices. You would have water ice floating around. You would have ammonia ice. You would have methane ice floating around because the sun's radiation would not be enough to vaporize these ices. So hydrogen gas plus heavy elements. Remember, we're always assuming that this is not a sun, our sun, made out of only hydrogen and helium. We're assuming that there were lots of generations of stars that came before us, and they were generating the heavier elements. We estimate that perhaps 2% of everything in this disk surrounding the sun, 2% was the heavy elements. So 98% of what was there, hydrogen and helium. But 2% was the heavier elements, carbon, nitrogen, etc., oxygen, all the way up to the heavy elements that we know and love in the Earth's crust. But this idea of a frost line is effectively the dictator that says that's why you have big planets to the right and small planets to the left. It's where the ices can form. So if we think about it very cartoon sort of style and think about how fast things grow, there's size on the vertical scale as a function of time on the horizontal scale. We think the Earth grew at a particular rate because the Earth grew in an environment where there was essentially no ice. It was only surrounded by gas. So it was only gas that could come together and a few heavy elements to form the Earth. But objects like Jupiter, they were outside the ice line, and so they had shed loads of ice to hoover up. As they went around the sun, they were literally collecting all of the ice, the water, the methane, the ammonia ice, and therefore any planets outside the frost line accumulated matter much faster. And so you get, perhaps for the first million years, it doesn't make a lot of difference, but then for the remaining millions of years, Jupiter really goes fast. It really collects, and the more it collects, the bigger its gravity. The bigger its gravity, the more it collects. There's a snowball effect, if you'll excuse the pun, as it moves outside the frost line and collects all of these ices. So that's what we think was actually going on. Again, on the same timeline that I was showing earlier, far from being the rocky ones, the small ones developed first, and then it got bigger and bigger and bigger. We think actually Jupiter started to develop very early, and then Saturn, and then the ice giants, and the rocky planets didn't actually come along until much later. I've indicated here Theia just to remind people that where did our moon come from? Our moon came along because a hypothetical planet called Theia hit the Earth and sloughed off a huge amount of material, which eventually became the moon. And that occurred towards the end of the Earth's formation there. But simply saying Jupiter came first doesn't again tell us exactly how we ended up in a solar system that looks the way it does. There's still some questions that we have to address based on the solar system that we observe now in terms of can we explain them in terms of the model or the simulation that we think applies. Some of the questions we need to answer is, where did the Earth's water come from? If the Earth was made in an environment where ice shouldn't exist and all the ice is Jupiter and beyond, how come we've ended up with oceans? Where did that water come from if the water didn't exist in the first place? So we've got to explain where the water came from. And there is a thing called the late heavy bombardment, a bit of an odd phrase, but basically we are fairly sure that there was a heavy bombardment in the early solar system which came along not when the solar system first formed, but probably hundreds of millions of years after the solar system formed. So whatever we come up with as an explanation for how the solar system came to be, we have to explain why there appears to be a period of heavy bombardment in the early solar system that came hundreds of millions of years after the solar system was born. We also have to explain a very simple observation. Mars is small. Mars is only about 1/10 of the size of the Earth. Venus and Earth very similar, but when you move out, suddenly Mars is about 10 times smaller in terms of mass. So why did Mars not grow the same way that Venus and Earth did? Mercury, you might say, well, maybe that's really odd because it's so close to the sun. But Venus, Earth, Mars, why are they not similar? Venus and Earth are very similar in terms of mass. Mars is very low mass. Ideally, we'd like an explanation as to why Mars didn't grow. How come it's on Earth if it's not on Mars? Yeah.
Well, I'm only assuming we had the water, but they didn't get any.
Well, okay,
So
why not? Yes, yeah. Yeah.
So we need water to grow.
Apparently not. The water came afterwards. Yeah. That's why we're all small compared to Jupiter. And we also have to explain, if we have a Kuiper belt of lots of icy objects outside the orbit of Neptune, why are they there? It's not a question necessarily of why are they there, but why is there so few of them? Because we might expect when the solar system formed, there were huge numbers beyond the orbit of Neptune, but they seem to have been dissipated. So where did they go? And what happens, and how do we explain the Oort cloud, a large spherical cloud which is responsible for comets? So I come back to the statement that this is all conjecture and this is all based on, here's a model that we can put forward that gives us a simulation that might explain how the solar system came to be. It's not proof, it's not proven, but it's a model that to some extent fits the facts. And that's what people have been doing for many decades, running simulations of, if we start with what we think the early solar system looked like, can we explain the solar system that we have today? A word about the late heavy bombardment. When we look at the moon, for instance, we see a number of craters, but some areas are very heavily cratered and some areas are quite definitely not. When we look at the Mare Imbrium basin there, this appears to have been covered with a lava flow which flooded and covered a lot of craters, and it's clear that it hasn't had much impact, hasn't had many impacts since then, because otherwise that mare, that lava flow would also be punctuated with lots of craters, just like we see in other parts of the moon. So by evidence like that and from Apollo rock samples, there is evidence that the moon was pulverized about 4 billion years ago. At least 500 million years after the solar system formed, the inner solar system, the Earth and the moon, and probably all the planets in the inner solar system, got pulverized with lots of objects. We don't see it on the Earth simply because of the weathering systems on Earth have got rid of that, but they are preserved on the moon and Jupiter, and we can't really tell what's going on Venus. So any hypothesis we come up with has to really ideally explain the late heavy bombardment. Some people query this because some people say this is actually, well, maybe it wasn't simply an enormous increase in the flux of things 4 billion years ago. Maybe it's the result of statistics. Maybe it's the result of the fact that we've only landed at a finite number of places on the moon, and we've got a few samples of moon rocks, but we haven't got moon rocks from all over the moon, only at the landing sites where the 6 missions have landed. So some people are saying maybe this is biased by the evidence that we have, but still it's the only evidence we have, so we're working with that. So coming back to this idea that Jupiter was formed first and Saturn and ice giants and then the rocky planets, if we want to answer why a late heavy bombardment 4 billion years ago, why does the Earth have water when the water should be beyond the orbit of Jupiter, then people came up with different models and different hypotheses. And these are hypotheses that are being checked by research, not necessarily proven. One of them is the Grand Tack, which explains what happened to the early solar system particularly the orbits of Jupiter and Saturn. And a different model looks at what happened millions of years later, hundreds of millions of years later, called the Nice model. Not the NICE model, the Nice model, because it's the University of Nice. So they are different time periods. One is what happened a million years or so after the solar system formed. The other is hundreds of millions of years. So remember, this time scale is rather compressed. So let's first look at the grand tack, which affects Jupiter and Saturn, and then we'll look at the Nice model, which affects all of the outer planets. So the grand tack, you know what a tack is in the nautical sense, when a boat moves one way against the wind and then it has an abrupt change of direction and moves in another direction relative to the wind. So a tack is an abrupt change of direction. We think that happened with the sizes of the orbits of Jupiter and Saturn. So here's a simulation. The simulation is a bit difficult to follow because of the speed at which the simulation runs. So I'll run it twice and then step through it so you can see it a bit more clearly. We're starting with an inner solar system where we've got Jupiter, inner planet there, Saturn, Uranus, and Neptune. And the red indicates a whole load of small rocks, planetesimals, with no water. So basically everything inside Jupiter is dry. There's no water in there. So the red is just lumps of whatever. The dust grains have collected into pebbles or rocks, but there's effectively no water. Everything outside the orbit of Jupiter is maybe the same sort of stuff, but now it's got loads of ice in it. Let's not worry about whether the ice is water ice or methane ice or ammonia ice. It's just ice. So let's just call it water. So the red stuff is dry, the blue stuff is wet, if you want to think of it that way. Technically, they're called S-type and C-type, but we're not going to worry about that. It is thought that if we run a simulation, we can work out what would happen to Jupiter and the other planets because they will interact with all of these objects. Yes, all of these objects are tiny, but there are lots of them. So the total mass of all of these, if you like, rubble that's sitting around in the universe, although the individual boulders or pebbles or tiny asteroids themselves are very small, when you've multiplied them by the fact that there are billions of them, there is a significant gravitational attraction between each planet and all of these objects. Trying to calculate what would that do is quite tricky, but it is believed that it would result in a change to the orbit of Jupiter. And we run the simulation, notice that the Jupiter orbit is shrinking. And as it goes through, it's bulldozing through all of the red stuff. It's effectively scattering all of the dry objects from the inner solar system. And almost too fast to see was the fact that Saturn followed it in. Now we've got a situation after 500,000 years or so where Jupiter and Saturn orbits have now expanded back out again. But let's run it again so you can see Jupiter is shrinking, bulldozing its way through the red stuff, and then Saturn, the next one out, shrinks into Jupiter and effectively pulls Jupiter back out again. This is really weird. Why the hell should Saturn go in and why should the pair of them come back out again in such a dramatic fashion? So let's just look at that mid-tack. There's Jupiter and Saturn very close in, roughly speaking, where Mars would be. In other words, Jupiter and Saturn have gone ploughing into the inner solar system like snowplows and effectively have removed a lot of the material that would have been used by Mars to make itself bigger. At the end of the tack, Jupiter and Saturn are now a lot further out, perhaps fairly close to where they are now. And Uranus and Neptune, notice, are actually way outside this original field of view. This field of view is basically just 7 or 8 astronomical units. The Mars orbit is depleted by that action of Jupiter's orbit shrinking and then eventually expanding back out again. So in other words, when the rocky planets did form, the Earth could mop up some of the rock that was around, but Mars had very little to mop up because most of it at its radius from the Sun had been disturbed by this tack of Jupiter coming in and then going out. So let's have a look at it step by step because the animation is interesting but far too fast to see what's going on. So it is thought that because Jupiter is interacting with all of these bodies, especially the ones outside its orbit, that tends to make the orbit of Jupiter shrink. We're not going to go through the dynamics of why it works out that way. That's what the simulations tell us. So the orbit of Jupiter shrinks and Jupiter migrates inwards, and notice that a lot of the red stuff is now scattered outside where it used to be. There's a lot of the red stuff now in the asteroid belt. Stuff that was rocky and relatively dry, we now find in the asteroid belt. Saturn does the same. Saturn also is interacting with all of the material in the dusty ring of the solar system, the early prototype solar system. But Saturn is a little less massive, and for reasons I'm not going to go into, it is thought that Saturn actually migrates faster as it comes in. And it goes very fast on a very short time scale, only thousands of years. We're not talking about millions of years. It only takes Saturn thousands of years to migrate inwards. And in doing so, it also is snowplowing its way through any material that's there. As a result, remember, Jupiter shrank because of all the material around it. But Saturn has now cleared all that stuff. And as a result, there's less stuff outside Jupiter's orbit to make it shrink any further. So Jupiter doesn't shrink any further. Once Saturn catches up with Jupiter, it actually results in the opposite migration, because now there's lots of stuff inside the orbit, not much stuff outside the orbit. That results in a tack as a change in direction. And both Saturn and Jupiter now migrate outwards and end up further out than they started. So not only have we repositioned Jupiter and Saturn, we've also repositioned a lot of the rocky material that used to be in the inner solar system, much to the chagrin of Mars, that now isn't able to grow any further. So that's what happens when the so-called grand tack finishes. So that at least explains to some extent why it is that Jupiter has affected Venus and Earth and Mars, and in particular why Mars ended up rather small, because it was on the outer part of the rocky planets. It was the first one to be affected by the migration of Jupiter inwards. In other words, Jupiter is a bit of a bully. That doesn't explain where the water came from. Why did we end up with an ocean full of water, lots of oceans full of water? Somehow the ice that's out there in the outer solar system ended up coming into the inner solar system. And that's what the NEAS model is trying to explain. The NEAS model is a model of what happened at a much later stage, after Jupiter, Saturn, Uranus and Neptune have done their thing, after the rocky planets have formed. Then it's an explanation of what happens as a rearrangement of the outer solar system, especially the Jupiter, Saturn and the two ice giants. Again, a simulation. It's difficult to see what's going on here, so I'll talk you through it. We've got Jupiter, Saturn, Uranus and Neptune. For those of you who are really eagle-eyed, you might notice that Neptune is inside the orbit of Uranus. It is thought that in the early solar system, Uranus and Neptune were the other way around. So in other words, my clockwork orrery is nothing like a real solar system. The solar system is dynamic and chaotic and can result in planets rearranging themselves. Certainly the simulations say it's possible. Whether it actually happened or not, we're not sure. But this simulation started with a very dense disk, which is looking at other solar systems, looking at other protoplanetary disks. This is what we think the solar system started like. We've got the rocky planets, which I haven't shown, and we've got the gas giants and the ice giants there, and we've got a whole load of small rock and ice planetesimals, roughly speaking, where we might expect the Kuiper belt to be, but much more dense. So what actually happens when they run this simulation? Well, not much happens for millions and millions of years. You'll see a little bit of jiggling as the calculation works out how these planets will go around the sun. Remember, Jupiter's going to go around the sun, but it's going to get pulled by Saturn. Saturn's going to go around the sun, and it's going to get pulled by Jupiter and the ice giants, etc. Nothing much happens for a while until there happens to be a slow drift of the two main planets, Jupiter and Saturn, And at some point, they get into resonance with each other. In other words, two orbits of Jupiter happens to line up in time with one orbit of Saturn. And when that happens, they can really tug on each other time and time and time again. Whenever they are synchronized in some way, a so-called resonance, then any tiny tug adds up every time they do one orbit. And that results in a chaotic change to the rest of the solar system. Let's see it run. So nothing much happens for a little while, a little bit of jiggling, nothing much happening. Jupiter and Saturn are going to change ever so slightly until they hit resonance, and pow! On a very short time scale, Jupiter and Saturn get into resonance, they suddenly start pulling on each other, and they suddenly start affecting the ice giants, which then get pushed out into the outer part of the solar system. What's happened to all the icy particles? Again, they have been completely and utterly scattered by the movement and the change, the migration of these planets. Where do most of these icy particles go? Some of them get thrown out into what we now call the Kuiper Belt. Some of them get thrown out so far they end up in the Oort cloud and produce a large spherical cloud around the solar system. Some of them go in. And if you calculate how many of those icy particles get thrown into the inner solar system, well, in principle, it's enough. If you work out how many of them would land on Earth, it's enough to make the oceans. So it is possible that the water that we see on Earth actually came from ices in the outer solar system, and the late heavy bombardment was a result of this interaction of Jupiter and Saturn occurring something like a few 100 million years after the solar system, sending lots of things into the inner solar system. The moon ends up getting cratered 400 or so million years after the creation of the solar system, and also, luckily for us, brings water to the Earth as well. So a reminder that the planetesimals that were originally in a big green disk around Jupiter, Saturn, Uranus and Neptune, now we have much larger orbits, and all of these little icy bodies have been scattered either into the inner solar system, that's what we call the late heavy bombardment, or possibly ejected into the Kuiper Belt or the Oort cloud. So that, in a nutshell, is what we think might have been the history of the solar system, given on a rather expanded timescale here. Of course, it's only approximate in terms of 1 million, 10 million, 100 million years. But just to try and put things in order, we think things grew like this, and ultimately it was disruptions of the solar system because of the Grand Tack and because of what we think of as the Nice model. Those were responsible for dramatic changes and complete rearrangements of the solar system, in the sense that it was so dramatic, planets would be not necessarily colliding with each other, but certainly swapping orbits. Of course, that's not something we see now, but the solar system now is effectively stable in the sense that on timescales of millions of years, it looks like all the planets are quite happily going round in relatively circular orbits. None of them are in resonance that will cause any of these dramatic changes. And we think that these resonances were certainly one of the possibilities that explains why we ended up with the solar system that we see today. Some people are not happy with the Grand Tack. Some people are not happy with the Nice model. People are still running simulations to say, well, it might have happened that way, and that might explain the water and the late heavy bombardment. But there might be other explanations which are equally good at explaining the heavy bombardment and the water. So you should treat this as just one of potentially many possibilities for explaining how the solar system came to be. Thank you very much.